Okay, today we're going to talk about a new thing, which is non-invertible chiral symmetry. And I believe that nobody has yet talked about non-invertible symmetry in this school, so this will be your first example, which is good because it is, in a sense, the most elementary, non-trivial example, even though it's not very elementary. So our setting will be 3 plus 1D U1 gauge theory. So just like yesterday where we had this toy model. And F will be the field strength. It'll be D of C throughout this, and C is the dynamical gauge field. We're envisioning the situation when there is a classical U1 chiral. I emphasize the word classical here. Global symmetry. J will be the current. So classically, D star J is 0. It's a conserved current. That's why we're talking about it. But generally, J is not conserved at the quantum level. So generally, we'll be interested in this type of equation. D star J is n over 8 pi squared f wedge f. This is the so-called ABJ anomaly, Adler-Bell-Jaquiev anomaly equation. N here is an integer.
Do you need to have matter field or have the current? Or?
Yes, I haven't yet said anything about the matter or other things like that. I'm trying to present it in a way that makes it clear that it's very general. All that we'll need for this discussion is a current obeying an equation like this. But indeed, let me address that by giving you some examples. There are many, but some to keep in mind. So the first, as suggested, is massless quantum electrodynamics. So just as yesterday, we have some fermions, chi plus minus A, gauge charge plus or minus 1, and A going from 1 to n. What is this chiral symmetry in that case? Well, it's the current that sends, say, chi plus A to e to the I theta chi plus A and does nothing to chi minus. So classically, that's a symmetry of the action. And there is an anomaly in a flavor gauge triangle. So this kind of diagram. Here is J. And now here is this field strength operator F, and this is proportional to n. Now note the similarity to what we were doing yesterday. Yesterday we were also considering triangles, but the vertices were different. Here we have flavor, gauge, gauge. Yesterday we had flavor, flavor, gauge. So the implications of triangle diagrams are very different depending on what the legs are. So that's one example. Another example, axion electrodynamics, which we briefly talked about yesterday. So the axion is a periodic scalar. And we couple it to the gauge field, as so. Unfortunately, I called NK yesterday. Like that. Oh, sorry, thank you. Okay. Mu. Thanks very much. And J is the shift symmetry now. So the current J is dA. And it obeys the same equation with the same n. So those are two examples. There are also, I shouldn't bewitch you into thinking that there are only examples in abelian gauge theory. Those are the most accessible examples because everything is what you see is what you get. There are also non-abelian gauge theory examples, UV complete examples, where there are discrete analogs of that equation. But I don't want to get into all the technology needed for that. You can read about it somewhere else. So we'll do these accessible cases. So there's this anomaly coefficient n that appears all over the place, and we could do things for general n, but it makes our lives a little more complicated for the purposes of a pedagogical presentation. So from now on, n is 1. So we don't have to think about n anymore. Now what's the puzzle? What's the reason for the talk? Does J obeying d star J equals 1 over 8 pi squared f wedge f? This is such an important equation, we'll call it equation star star. We'll keep coming back to it. Does J obeying that generate a conserved charge? Depending on your point of view, you may adopt several answers to this question, and each of them seem reasonable. That's why there's a puzzle. So in the no camp, there is the kind of elementary reasoning, which is that the current J is not conserved. So if you compute correlation functions, you don't find a conserved current. And surely for a continuous symmetry, you need a conserved current. So from one point of view, you should stop the discussion here. But there's a yes camp as well. The leader of the yes camp is Tuft. who I believe should really be credited with this kind of observation. So despite this divergence, let's push on and see what we can make of it. So let's examine a formal charge. So I just ignore this divergence, and I just try to write a charge q. It depends on time. It's an integral, say, over all space, which in this level of analysis we just take to be R3 of J0 of xt. So here we could think that space-time is R4, Euclidean space-time. Okay. Let's consider this charge evaluated at time equals infinity minus the charge evaluated at time equals minus infinity. So the net violation of the charge. Okay. This is, of course, the integral dt of q dot. And now I write this as the integral d4x over space-time of d star j. Here in this move, I've added, or dropped if you like, a total spatial divergence. So I'm assuming something at the boundary conditions in space. But that seems like a typical innocuous move. Now we use this equation. Right? Usually we'd say d star j is 0. There's no net violation of charge. D star j is not 0, but we know what it is. Okay. This is equal to 1 on 8 pi squared integral over space-time of f wedge f. Now, what kind of mathematical objects are appearing in this integral? Well, f is a differential form, but if we look at its equivalence class in cohomology, f over 2 pi is somebody in H2 of space-time with coefficients in z. Meaning that it's something that if you integrate it over any closed 2 cycle, you'll always get an integer. Now, if we're on a topologically trivial space-time, for instance, we could be considering our R4, which we regulate. Typically, we have to say a little bit more sophisticated thing, so we regulate it as a big 4 sphere. Then there are no 2 cycles. There is no topologically non-trivial flux, and that is a integral which is sampling whether this f defines a topologically non-trivial class. So this implies the right-hand side vanishes. So, for instance, it seems to mean that the chiral symmetry selection rules hold. At least in 2 contexts: local operator correlation functions kind of your bread and butter calculations, as well as standard S matrix elements. So that's the yes camp. It's a little bit more sophisticated in argument, but you see that despite the anomaly equation, there is something conserved. Now, the paradox remains, though. I mean, even if you adopt this yes point of view, it's clear that the selection rules can be violated. So let's say how that would work. So for instance, when I get to this key step where I have to integrate f wedge f over space-time, what if my space-time is more interesting? So if I have a rich enough space-time, I need some 2 cycles. For instance, S2 times S2. Then I can make that integral non-zero. And f, the gauge field, is summed over, so it's not even a fixed value. Depends on which term in the sum you're at in the path integral. Now you may say, don't talk to me about S2 times S2 space-time. I'm a simple person. I only like R4, S4. This is also kind of reasonable. But you can't escape this kind of space-time. It could be back to our simple space-time, like S4. But now we'll insert tuft lines. Okay. Remember a tuft line. So here's a tuft line on L. Here is a linking 2-sphere. I'm sorry I can't draw pictures in 4 space-time dimensions. But the tuft line is characterized by the fact that the integral over S2 of f over 2 pi is equal to m, which is the magnetic charge. So this is a disordered definition of an operator. We modify the fields that we integrate over to have this behavior. That counts as inserting the tuft line. And the basic point is that this kind of operator insertion, well, it's creating a 2-cycle. It's creating this S2. So even if you are interested in only doing quantum field theory in S4, as soon as you exit the class of correlation functions described just by local operators, but you start considering line defects, then you're going to feel a non-zero integral there in general. So here are the operator insertions, and line operator insertions. Are creating topology for us.
Can I ask the question, like when you are talking about like correlation function of local operators, you could have acted on say 2 U1 currents and acted on this charge, which have a contact term and still can give still can violate the selection rule or not, because of the contact terms in like the chiral U1 current.
That's this anomaly equation. That contact term is precisely this diagram, which integrates up to that equation.
Right.
So I'm telling you that that contact term is not enough to violate. Like if you just consider local operator correlators, you'll never see any violation. Questions about this basic puzzle? Yes?
Local correlators on R4, is it?
On R4, yeah.
Like on T4 you could make...
On T4 you can do it, yeah. Yeah. What I meant by correlation functions of local operators, I meant specifically in R4, S4, like kind of the standard setup where you would compute them. If you consider with periodic boundary conditions, you would indeed sample that.
Why did you call this a paradox?
Well, it's a paradox. So my view on the paradox is that you want to develop a notion of symmetry which is sophisticated enough to incorporate this yes answer, give you this kind of selection rule here, but also produce that answer somewhere else.
I see.
Right?
Okay. So your point is that if there is a selection rule, there should be under symmetry.
Yeah, exactly.
You can ask,
There is some notion of symmetry here. I mean, this argument by Tufte is right. There is something conserved. It's just more sophisticated than the standard quantities that we consider. And so our goal is to develop a language for saying what that is. More questions?
So Equan defined like non-gauge invariant current operator by including this.
I'm going to talk about that in a minute. So wait, yeah, I'll make some comments about that. Any other questions? Okay.
Could instantons can we consider instantons in this equation?
We are considering them in a sense. You know that this equation here, right? This is trying to sample the instanton density, right? But the point is, in S4, there are no abelian instantons.
Yeah.
That's what's happening.
Yeah, yeah.
Right? Maybe it's important to say that's why it was important that this ABJ anomaly, the right-hand side, is the square of something.
Yeah.
If it's the square of something, then you can say that there aren't any terms saturating the equation in a sufficiently simple spacetime. If I had upgraded this straight away to a non-abelian gauge field, like an SUN gauge field where I had a trace, then in S4 there are instantons. No confusion. The selection rules are violated even in local operator correlation functions in trivial spacetime. So there's something special about the fact that this is a square. Okay, so the key clue that we want to take into account here is this fact that it's a square of something. And I remind you that f is not a generic operator. We have that df equals 0, which by now you know means that f is a current. It generates the U1 one-form magnetic symmetry. So the anomaly equation star star is trying hard to be a current algebra. Right? This is a current on both sides. So we'll try to use that to develop an interesting construction. And it will take us quite a while to work out all the details. Okay, so we've set up the puzzle. Hopefully I've motivated the problem. And now we're going to start on our long slog, which is the construction of non-invertible symmetry. Okay, so modern definition. Our modern working definition of what is a symmetry, at least from the viewpoint that we need here, it's just the same thing as a topological operator. This works at least at the level of slogans. So our goal today, therefore, is to define a topological operator for J obeying the ABJ anomaly equation. Now, without the anomaly, this is easy. So let's first do that, and then we're going to have to modify it somehow. So if I first drop the divergence, we just define the exponentiated integral of the Hodge dual of the current. Let me give this some notation. We will call it U alpha of M3. What kind of beast is this? So it generates finite transformations with angle 2 pi alpha. It is defined on a closed codimension 1 manifold M3. Makes sense. We're trying to define a zero-form symmetry. We're in 4 space-time dimensions. M3 you could think is like a spatial slice where you want to act. It is topological for any alpha. What does topological mean? It means that if M3 is wiggled, is changed continuously without crossing other operators, then the correlators are unmodified. We should write one more rule, which is what happens if M3 crosses another operator. If M3 is moved, say, to cross a local operator, it acts by the symmetry transformation. So let's draw a picture. Here is our M3. and here is some local operator O. Now this M3 is the support of this extended operator U alpha of M3. So you try to move it. You can do little wiggles, no cost, but when you move it across O, something happens. Pick up a phase. Where Q, of course, is the charge. So that's the standard construction of topological operators given a standard conserved symmetry. We're going to have to modify it somehow.
Clint, can I ask a question?
Yeah.
Can you explain, one could say, well, this is a bit tautological. We could say that take this last equation as a definition of the topological operator.
Yeah.
And then I'm going to miss something. But is it really important that this topological operator has an independent definition as the integral of a current exponentiated?
Yeah, that's a great question.
Or is it just like, well, that's all there is?
This is something akin to asking about proving Noether's theorem, right? Like imagine I give you a family of operators U alpha of M3 obeying these axioms. Could you prove that there's a germ of it, that it's really an exponentiated current integral, that there's a local operator hiding there? I don't think there's a sufficient demonstration of that in the literature. Yeah, so I don't know of a way to go backwards exactly at a rigorous level. It would not be surprising if there is an argument, but you might come up with some challenges also.
But I was asking a more modest question, like the fact that this operator is going to have that in expression, is it going to give you any extra value?
Well, in the case that I'm going to do, it'll be important for me to know what d star j is, because I need to know the fact that the current is conserved is what gives you that this operator is topological. So the fact that I know what d star j is telling me by how bad it's not topological. So in this case, it's sort of important. More questions? Hopefully you've seen this kind of presentation before. Okay. So that was everything. Just a little summary of symmetry transformations and symmetry operators without the anomalous divergence. Now, for J obeying our fancy equation, the anomaly equation, let's consider first a naive current. This was already suggested by somebody in the audience. So star j minus 1 on 8 pi squared c wedge dc. It's not so naive. You could even find this current written about in Weinberg's textbook. So you're in good company if you think this might be a good starting point. This is conserved. Right? The derivative of this, remember that dc is f. So these two cancel each other when I take d. So you might say, well, don't tell me about anomalies. I'll just look at. So I could ask, does this expression Does this make sense? If something like that makes sense, we are in business. I'm going to tell you. Okay. So far I said it's a question, right? I put a question mark there. I'm not going to, exit the room now. Mic drop, Okay, so it's formally topological. This is all a bit formal. To prove that the operator is topological, you need that the thing that you're integrating in the density, this density here, is conserved. Okay, so formally that's conserved. So, okay, we're somehow on our way, but it's not gauge invariant. So that sounds like a huge problem. Now let's try to be more clear about this not gauge invariant point. So the problematic term from the viewpoint of gauge invariance is this alpha over 4 pi integral over M3 C wedge dc. Right? The integral of star j is definitely gauge invariant with any coefficient because j is at least a well-defined operator. The problem is this term. And even more specifically, you can see that it's trying to be a Chern-Simons term, but with a very funny level. Okay? This is even the right normalization. So this is using Chern-Simons level alpha. So when can we make sense of that? Well, your first thing would be to say, well, Clay, I know we can make sense of integer level. So alpha in Z, that's definitely okay. Integer levels are okay. Right? The integer level Chern-Simons term is definitely gauge invariant. This is okay, but sorry, you strike out. You strike out because when alpha is an integer, this is a complete 2 pi rotation. Right? Remember, this u is defined to be a rotation by angle 2 pi alpha. So if alpha is an integer, it's the nothing operation. Okay. So that's not good enough. So the novelty, which is really only a novelty to people in high energy physics, in condensed matter it will be more recognizable, is that in a sense alpha rational also makes sense. Now I'll have to explain a lot to convince you of that. But from the viewpoint of constructing an operator, this is the key insight, is that we will be able to make sense of this expression somehow when alpha is a rational number. Questions?
When alpha is in Z, then is this indeed like the nothing operation? It seems to be something.
No, it's like doing a rotation by 2 pi alpha. So if all the charges are quantized, it's just nothing.
Mm-hmm. But does it have some inclusion like extended operators or something?
I don't think so. If you thought of it like on the field, it's literally doing nothing to the fields. Yeah?
If you can make sense of rational alpha, why can't you then take limits and make sense of any alpha?
Yeah, good question. You'll see sort of how it works in practice when I say what I'm going to do here. But there won't really be any kind of continuity for nearby q. So the operators will look sort of very different for different rational numbers. And that's kind of a weird thing. So I sort of did a dodge here, which maybe you're calling me on, which is that I first asked about this current, and then I quickly plugged it into the exponential. And this was also actually a maneuver that people didn't really notice in the past, which is that if you try to define a current, you will quickly get stuck. There's really just not going to be any improvement of this operator as a current that's going to be conserved, or we're not going to find anything like that. What we are going to be able to do is make sense of these finite transformations for specific alpha. But there's no guarantee that these finite transformations look continuous in that parameter. And they won't.
But can you define some weird metric on numbers, some periodic stuff?
Maybe you can. But maybe you'll see. I mean, that it's not so easy. Okay. So, the rational level. The rational level it makes sense as a response. And we'll unpack that word response. But I want to emphasize, it's not an invertible theory on its own. The word invertible just means classical. So here, in a sense, the fact that alpha and z was OK, what that meant was that then CD, this Chern-Simons term with alpha and integer is just a well-defined classical term. It's a well-defined phase. When alpha is in Q, this is not exactly a well-defined functional, but we can get it as the response to a path integral. So let's consider for example, U1 level K Chern-Simons theory on M3. So I can consider the functional integral dB. B will be the Chern-Simons gauge field. For right now, you can just ignore the fact that this M3 is eventually going to be the same as that M3. This is just a comment about Chern-Simons theory. So I write the standard Chern-Simons term with level K. But now I'll also couple this Chern-Simons gauge field to what, from this viewpoint, is a source. The source is C. So this is a partition function. We'll give it some notation. It's zk of depends on dc. So here C is background in this calculation. And B is dynamical. And I'd like to stress that for general K, this is a non-invertible TQFT. It has many operators, many states on a general manifold. But let's consider something special. M3, we take it to be S3, something very trivial. And I have no operators inserted. So the Chern-Simons theory has various Wilson lines. We can consider complicated correlation functions with them. But let's not do it. Let's just, for the moment, take M3 to be S3 and just evaluate that partition function. Then, you see, in this case, because there's no interesting topology on S3, B and C are no longer connections, but they become one forms. All gauge fields are all U1 gauge fields are topologically trivial on S3. So now it becomes very easy to do that path integral, right? Just a quadratic action of one forms. Okay, so you can compute this zk. I'll put S3 here to remind us that we're computing that. This can be computed by solving the equation of motion. Okay. After all, it's quadratic action. So the equation of motion tells us that B is equal to minus C over K. That's good. B is the dynamical field. C was a source. So this just tells us what the dynamical field is equal to. And you just plug in, and you get this zk S3 of dc. Well, it's equal to the exponential of minus I over 4 pi k integral C wedge dc.
How many terms? One loop term.
The one loop term, you mean like an overall prefactor here? Yes, there is a prefactor there that you need to be a little bit careful with, but you can regularize it so that it is a pure phase.
So it's always like a local counterterm can be removed.
Yes.
No, right? There is a G, this S3 partition function.
The gravitational Chern-Simons term, you mean?
Well, there is the gravitational Chern-Simons, and there is also the S3 partition function, right? Which is like log of the basically quantum dimension.
Sorry, you're right. There is a you're right, Max. There is a meaningful overall constant here. Yeah. Which will come back actually. Yeah. Sorry. Yeah, my mistake. Thank you, Max. Yeah. Yeah, sorry. The thing I want to emphasize here is this phase, though. It's this phase which we can formally we get in this simple case.
This is all dependent on C, so the constant is C independent.
Yes.
Okay.
Okay. So. Again, examining only the dependence on C, let's note that there's something like an effective Chern-Simons level. One on K. Now that was, of course, specific to the fact that we considered this very trivial not trivial, but simple space-time configuration, S3. And on general M3 instead, this zk m3, we can think of it as defining what we meant. By level 1 over k. So we might not be able to do this simple complete the square trick in general. There might be real gauge fields to sum over. So we just adopt that this is the right definition in general.
Is there a problem that now 1 over k is not integer, so we don't have is invariant under large gauge transformations?
Well, this formula is really only literally true on the 3 sphere, in which case there aren't any large gauge transformations to consider. Now, when you're in the situation where there are large gauge transformations to consider, then you just say, well, I just use this path integral. That's actually well-defined. That's a well-defined function of C. Yeah?
Are there possibly different things that you could have started with that integrate and give you the same?
Absolutely. Great question. So I here did U1 level k. Why don't I do something more sophisticated, more complicated TQFT, which gives this same result? There are many. But there's an interesting theorem, which I'll mention to you since you asked, about something kind of universal about this U1 level k, which is that any additional TQFT, any other TQFT which has this same eventual coupling to C, you can think of it as this U1 level k times something that doesn't couple to C.
That's probably only true if the TQFT is an abelian transform, right?
No, I don't. Okay, it's definitely true for abelian anyons. For non-abelian anyons, I thought the one-form anomaly allowed you to decouple a minimal abelian TQFT in general. Okay, let me retreat to the safe thing, but let's talk about it. I'm actually, yeah, okay, yeah. But definitely for an abelian TQFT with a completely general level matrix, you know, if I had, instead of having just B, imagine I had B1, B2, blah, 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 Bn, some huge n by n level matrix. It's definitely true that I could factorize that into this kind of this minimal unit times something that isn't talking to C. Max was very gently steering me towards a more correct statement. The question was this factorization. Does it hold only if you assume that the whole theory is abelian? It definitely holds then. Or can it also hold if the theory is non-abelian, which we might be going to have a discussion about. Okay, but from the viewpoint here, the most important thing is that we found 1. Right, we're still on our long slog trying to construct some operator. And the most important thing was that we found some topological partition function, which gives us this response. Some way of making sense of fractional Chern-Simons level. Okay. So now we're going to define a composite topological operator. So we'll call it D 1 over k of M3. It's defined in this way. I take U 1 over k of M3. And I have here also this zk M3 of DC. we could say that it's a path integral, an integral dB of, okay, the first term is just we're rotating by with alpha equals 1 over k, so we have integral star j. The whole action is on M3. And then we also have this Chern-Simons contribution. Like so. Now this, I did it here for alpha. This was the case alpha equals 1 over k. It's easily generalized. To alpha rational, though I don't really want to discuss it explicitly. So we succeeded. I wrote explicitly a formula for you for a topological operator, which looks at first like U with alpha 1 over k, so a fractional rotation. But it has this topological field theory dressing, this U1 level k coming for the Rhine. And you can generalize that to rationals. And for a while now, we're just going to unpack this big formula here.
So can I ask a question? So you're saying that if M3 were equal to S3, then we were in business all along. There was no need to. So that expression makes sense. But do we want to have access to more general topological operators than S3?
Well, good. This question comes back to, so if your goal is to discuss the action on local operators, you won't need this, this fancy construction. And I'll comment on that in more detail in a moment. But suppose you want to consider like correlation functions with line defects. Then, yeah, you need it. So it's a question of, it's really about which questions you're concerned with. But I want to have a formalism that can have selection rules that hold simply on local operators and also give me at the same time the right selection rules on line defects. So I'll write the selection rules also. It's somewhat interesting. Yeah.
Yeah, I don't think this will apply equally well to this chiral symmetry for the fermion and as well as this axion electrodynamics.
It works, yeah. Yeah, I mean, it works very generally. All I need, I mean, I gave you those examples so you have in mind which kind of problems we're thinking about. But all I need is some current obeying some anomaly equation. And even the discrete version of that anomaly equation will also work. So there's also this in certain non-abelian gauge theories also. Yeah.
Sorry, so I have a basic question. So you said that in this construction, B and C on S3 are just one forms, not connections. Does that mean that?
I still have the gauge redundancy. I have the gauge redundancy, but I just mean there isn't anything topologically non-trivial. There's no flux sectors to sum over.
Okay, so that's why when you say B is minus C over K, that doesn't spoil the holonomies of B or anything like that.
Yeah, exactly, yeah.
If our anomaly coefficient wasn't 1 but n, then you would have like a normal leftover Zn symmetry, right?
That's right.
You wouldn't have to do all of this.
That's right, yeah.
Do we gain anything then still from doing this? Like
absolutely. So if the anomaly coefficient was n, which I set to 1 at the beginning, then there's a Zn subgroup which isn't polluted by this ABJ anomaly at all. That's just a standard normal symmetry. And then you could ask, can I do rotations by general rationals? And again, you can by coupling to TQFTs.
Yeah. Is there a similar construction for the 1 plus 1D chiral anomaly?
For the 1 plus 1D chiral anomaly, no. let's go back to that equation star star, which I think has been erased now. D star j is f wedge f. The important point about that the thing that got started with thinking there was a symmetry, the 't Hooft argument, was to say on the 4 sphere with local operators, that symmetry, that integral can't be saturated. Now, suppose I look at the case that you were talking about, which I think would be d star j is f. Okay. Now, on the 2 sphere, we're in 2D, with local operators inserted, that can be saturated. Right? So there isn't any sort of selection rule to explain there. Yeah.
How are fusion rules affected?
Well, I'm going to go through. I'm going to compute them in great detail. So you have to wait. Yeah. Yeah.
Can we do the same thing with gravitational anomaly of the?
With
there is a gravitational contribution to the chiral anomaly, right? So if we play the same game with gravity, do we get a non-invertible symmetry?
You mean if gravity was dynamical? Yeah. Then you can have analogs of these games, and I think even Juven might have written a paper about it. Yeah.
Yeah. But that symmetry has to be gauged somehow.
Okay. So again, let's think about the anomaly, the anomalous divergence of a current, right? 3 different basic possibilities in 4 dimensions. Divergence of J is F an operator, wedge F an operator. That's what we're considering today. That's the case which you traditionally call the ABJ anomaly. It's not clear without much more comment whether there really is a symmetry. The possibility we considered yesterday was divergence of the current is F an operator times F prime a background field. That's the case where when you turn off the backgrounds, the current is conserved. So that's a kind of symmetry, but a weird one. That's the higher group symmetry. And then there's the final case. Divergence of the current is F a background, wedge F prime another background. Okay? That's what's called a 't Hooft anomaly. There's definitely a symmetry. There's an obstruction to gauging it.
Can this be done also for small f that is non-abelian, for example?
Yes, I mentioned that in passing but didn't write it. It depends exactly on what you mean. So if we just say upgrade the small f to an SUN connection, then we are not going to gain anything. And again, the way to see that you're not going to gain anything is go back to this 't Hooft argument. This is really what grounds you. Is there some selection rule on local operators to explain or not? Right? So if you just have like minimal anomaly coefficient and SUN gauge fields, there's nothing to explain because the SUN instanton density can be saturated in flat space. Or in S4.
Yeah. A local operator, local charge operator, that means that will give me a saturated.
What I mean is that the selection rules for the chiral symmetry, which is violated, which are in non-abelian gauge theory with a non-abelian ABJ anomaly, they're just completely violated by instantons.
Oh, I see.
Right, so there's nothing to explain.
Additional mode anything.
Yeah, there's nothing to explain. So now, if you start doing something more sophisticated, instead of having SUN, you have PSUN, then you're going to have a discrete analog of this story.
You mentioned before that you can do this whenever the anomaly is something squared. So if you have like something non-abelian in higher dimensions, like the second term class squared.
Yeah, I think you can do it. Yeah.
I mean, I think the higher dimensional cases are not fully worked out, but I think you can do it. Okay. We talked so long that my tablet went to sleep. Okay, so let's keep going. Okay, intuition. I'd like to give you some more viewpoint. This is kind of a mouthful, so let's develop some intuition about this. What's wrong? With just U1 over K from a more modern point of view. And how did this TQFT manage to fix it? Okay, so here's our M3, which I'll take to be just the locus where x is 0, some coordinate direction x is 0. here's x less than 0, and here's x greater than 0. Now, u, 1 over k, was the exponentiated integral of 2 pi I over k, integral on x equals 0, star j, like that, which I just write using Stokes' theorem. Don't check my signs. Of d star j. Now, what to do about that? Well, we can use our anomalous divergence equation, the hero of this whole talk. We can write this as the exponential of 2 pi I over k integral f wedge f over 8 pi squared. Like that. What is that? It's an effective theta term. So the issue with this u is that it's not a defect in a fixed QFT. Right, so x less than 0 and x greater than 0 are not the same QFT. The theta angle on the plus side is the theta angle on the minus side, plus 2 pi over k. So it's a mild difference, something that we're able to correct. To compensate this, by adding here a TQFT on this interface, that's what we did. And there were two key properties of this TQFT. It must have ZK one-form symmetry. So some particular abelian anyons. That's the first thing. And it must have an anomaly. Now, the anomaly of the one-form symmetry in a 3D TQFT is related to the spin of the generator. Let me first write the formula, though. So what anomaly do we need? So the inflow action should be, well, the kind of SPT term in one higher dimension, 2 pi I over k integral x greater than 0 B wedge B over 2. So B is the two-form background field for this one-form symmetry. So I think this means that the spin of the generator has to be 1 over 2k. So these are the key properties of the TQFT that I'm really using. And then I couple the bulk and TQFT by setting capital B2 here equal to F over 2 pi. So that's a more abstract way to think about what we did. Our problem with the naive thing U is that it creates a discontinuity in the theta angle. And we compensate that by coupling to a TQFT with a prescribed anomaly for its one-form symmetry. And then they talk to each other through the fact that the bulk gauge field strength can be thought of as the source for the one-form symmetry. Yes?
Can you have this one-form symmetry and this anomaly without having anyons?
Well, I'm trying to construct a symmetry defect. So I want a topological operator. So it's important that I was able to realize these considerations in a TQFT. Okay. More questions? No. It's all either too easy or too hard. Okay, I'd like to give you an alternative construction of the same defects. At least I'll sketch it quickly, which will enable us to compute fusion rules seamlessly. So I'll give you an alternative construction via half gauging. Okay.
Actually, Clay, did we prove the topological invariance?
Let me give you this alternate construction because then it's just so manifest that it's that's another reason for liking this is that it's.
Why is what you did not manifest?
I think maybe Max doesn't like that. I'm not sure, but maybe Max doesn't like that on not M3, not S3. It's not so obvious about the factorization and the topological nature. I'm not sure. I think this argument is an argument for the topological invariance, but let me give you another argument too. If you have two ways of explaining things, it's always better. Yes?
Can you just comment why is a problem to have kind of this interface of theta terms? Couldn't this actually be some nice construction of some symmetry defect?
Well, it's a topological interface. It's some kind of interface, not necessarily even topological. But it's definitely not a symmetry defect. A symmetry defect means a topological interface from a theory back to itself. Yeah, okay. So if that was my aim, then this U really didn't do the trick. Okay, so what do we do now for half gauging? So let's consider the following. Let's consider gauging a ZK1 subgroup of the one-form magnetic symmetry. So we're going to do a discrete gauging. By that I mean I'm going to take my theory with this ABJ anomalous J, and I'm going to sum over some zk gauge fields. And I'm going to see what happens. Okay? So we have to define this. How do you define it? So there needs to be a two-form gauge field. I'll call it beta 2. That will be the dynamical gauge field here. And their friend in 4 dimensions is a one-form gauge field. And what's the action? Should contain a term like I k over 2 pi integral d beta wedge gamma.
So is gamma 1 the same thing as C?
No. Sorry. Good. Yeah, sorry. These are going to be 2 new fields that are going to be needed to implement this. So why do you need 2 fields? They're U1 fields to make it everything really easy for us. But the reason you need 2 fields is that if they start their life as U1, they're not yet zk. So when I write this mixed Chern-Simons term, note that gamma just looks like a Lagrange multiplier here. So the equation of motion for gamma, so it kills the fluxes of beta. And also, if I sum over the fluxes of gamma, it restricts holonomy of beta to zk. So the point of writing this action term, this simple action, is that it's a way using U1 gauge fields to realize discrete gauge theory. So you get your hands on it fast. So in other words, beta is a zk gauge field. Not quite. So I want to gauge this zk one-form magnetic symmetry. Let me first do it in all of space-time. So we're going to modify the bulk action. What do we do? It becomes S bulk, whatever it was before, plus I over 2 pi integral beta wedge f. This means beta is sourcing this one-form magnetic symmetry. And then I have the term that I wrote before, ik over 2 pi integral beta wedge d gamma. Or perhaps I integrated that by parts. And then I'll write one more term, ik on 4 pi beta wedge beta. So this is the part that makes beta a zk gauge field. Why did I write this? This is like some discrete torsion. That's what high energy people call it. You could also think of it as some SPT. So here, beta and gamma are new dynamical fields. So I'm taking my bulk theory, I'm gauging a zk one-form symmetry inside it, and I have a particular discrete torsion. Okay. Let me go a little fast, so I'll do some things a little bit cheating, but not really. Let's solve the equation of motion for gamma and beta. So this implies that beta is minus f over k. And then I'll get rid of beta and gamma, so I'll integrate them out. You know, these fields, beta, gamma, it's a quadratic path integral. So basically doing the path integral just amounts to putting things back in, at least to see what's going on. We can do that here. So what we end up with is S bulk minus 2 pi I over k integral f wedge f over 8 pi squared. So what happened here is that the effect of doing this ZK1 form symmetry gauging was to change the theta angle. Variations on a theme here. So this ZK1 gauging sent theta to theta minus 2 pi over k.
Excuse me. When you integrate out, do you assume the bulk to be a S?
Yes, I'm just trying to get the effect on the bulk theory. If I want to be more sophisticated, I have to tell you why that is a correct maneuver on a general space-time. That you can do, but it requires more discussion, which I don't want to say. Okay, so we have this shift, and now what do? I use the anomalous chiral rotation. I do that everywhere in space-time, not in, okay? And then I can undo. The shift in the theta angle. Right? Probably you know when you have an anomalous chiral symmetry, if you do it, do that rotation in the path integral, it shifts the theta angle. Here I'm doing it to undo that transformation. And so what are you supposed to conclude from this? Conclude an interesting fact is that a theory T with this ABJ anomaly is invariant under gauging this ZK1 subgroup with, of course, appropriate torsion. This is a kind of self-duality. Usually, if you have a theory and you gauge some symmetry, it's an operation you could do, you get a different theory. Not so in this case. The ABJ anomaly equation, we can use it to prove that this theory has a self-duality under this finite gauging.
It relates to the twice gauging method for the non-liberal symmetry. So the twice gauging, so the TFT construction.
Sorry, what was your question?
So is it related to the twice gauging method for construction of the non-liberal symmetry?
Well, so I'm not assuming that everybody knows that method, but the point is to put all of those on the same footing. Yeah. Okay, more questions? Yeah.
Is there a way, like in the very first equation you wrote, like the conserved current, to see why alpha not rational would be bad? Like this thing that we did?
No, but you can get a clue from it, from the kind of guts of the construction. Suppose you start considering complicated, instead of just U1K, consider complicated abelian Chern-Simons theory with a general matrix of levels, this like n by n matrix. And you could ask, how complicated a number can you get here? At the end, you'll get some rational. There's some rationality built into that. So, if you want to make this defect by coupling to a TQFT that you might know, standard TQFT, it will always be rational.
I'm sorry. This is a very stupid question, but in the non-abelian case, okay, if I'm considering, for example, some manifold like RP2 plus RP2, where I don't have H4, so that all second Chern classes are vanishing, so I don't have this Stanton number, then their tough argument should work, right? Can I do this same construction there? No.
Sorry, there's non-trivial top form on any four manifold, on any closed four manifold. Let's be on orientable manifolds.
Yeah, because I think it's non-orientable.
Yeah, okay. I don't even know if you can put your theory on that manifold. That's a whole separate discussion, right? Whether or not you can put a theory on a non-orientable manifold requires some additional symmetry. In this case, a space-time time reflection symmetry. But if we just discuss orientable spacetimes, then every four manifold has a top form. Yeah.
Are you done with this?
No. I didn't construct anything yet. I just showed the first step. But actually, maybe I should stop. Yeah. Let me see. How much do I have to finish this part?
Yeah. Please don't go too much over time, because then we have the gong show, which is breaking at the seams a little bit.
Okay. Okay. So maybe then I'll take more questions. I'll stop here, and we'll use this self-duality to give an alternate second construction of the same defect in the next part. Okay.